Welcome to this new lecture. Again, we'll continue today with the Nyquist plots. So what we saw yesterday was or in the previous lecture was how to analyze stability in the frequency domain. So we answered several questions based on the Nyquist plot. The first question was what Nyquist would tell me is how many zeros are or how many poles of the characteristic equation lie on the right half plane. So that would be determined by the number of encirclements of the point -1 plus j0. And we also saw how we shift from the origin to -1 plus j0 and how -1 plus j0 analyzing this point will just help us getting the closed loop behavior by just looking at the open loop transfer function, right. And so what we will do today is to see or just handle some special cases, right. So what we said when we were defining the conformal maps from the S plane to the QS plane is that this map should not pass through any singular points or through any poles. But that's, well, it's mostly possible, but sometimes you could see that there might be a pole on the imaginary axis. Well, let us for simplicity say I just start with a pole at the origin. Okay. So the question we will ask is how do we handle these conformal maps or the Nyquist contour when the open loop poles are on the j omega axis. So if we use the Nyquist criterion directly, the S plane contour would pass through a singular point of 1 plus GSH, and this would just blow up. So this could be similar in a way to see, when we are doing the Routh-Hurwitz table of when you get an epsilon, when you get a 0, right, on in one of your columns. So one of the entries becomes 0. So what do? You just substitute with a very small number called epsilon. You assume it to be greater than 0 and take the limit as epsilon goes to 0 and then do the rest of the computations. So we'll do something very similar here. It's a little tricky here than what we did last time. Okay, so let's see how we will do this. So we need to make modifications so as to bypass these points in the j omega axis, and therefore what we will do is if there is a pole here, I just take a detour here, and this detour I will just say, well, I just take a little semicircle, okay, of radius epsilon. So this is how the semicircle looks, epsilon e power j theta, and take the limit as epsilon goes to 0, right. So if I just write it down a little more formally. So what we would have is take the semicircle indent around, say there is a pole at the origin. Okay. So if I just say this guy is a pole at the origin, I just draw a little semicircle, and S would now look limit epsilon going to 0, epsilon e power j theta. Okay. So as theta goes from -90 to +90. Okay, and then we'll just do this and then put this back here and see how the plot goes like. Okay, so just to get a little understanding, we'll start with the help of an example, right. We have a feedback system, I have a pole at the origin and another pole. So the sinusoidal transfer function, we just substitute S with j omega, and we know already why we do this, right. Why we just substitute S with j omega for the sinusoidal transfer function. Okay, so let's start by dealing with the pole at the origin. Right. The standard thing which I learned in the last class will not work because there is a singularity when I substitute x s equal to 0. Okay, so I take this little thing limit. So this guy, limit s or limit epsilon going to 0, this guy, this is the value of s. Now we will see how this value of s defined by this little semicircle given by this thing epsilon e power j theta, epsilon going to 0, and theta going from minus 90 to plus 90. So, how this little region will map to the QS plane? Okay. So, I take limit epsilon going to 0, k, what is S now? S is epsilon e power j theta, okay. Then I will have t, again epsilon e power j theta plus 1, okay. So, this guy becomes limit epsilon going to 0, I have a k in the numerator, epsilon, this guy goes to 0, and I will have e power minus j theta, okay. So, this guy k over infinity, k over epsilon, this goes to infinity as epsilon goes to 0, okay. And what does theta do? Theta varies now from, or this is minus theta, right, minus theta varies from plus 90 to minus 90 or plus pi by 2 to minus pi by 2, okay. So, I just first want to see how this little region here, okay, let us draw it a little better. Do this. This region, okay, I still can't get the line straight. This little region, right, so this is epsilon e power j theta. So, how will this map into the QS plane, right? S sigma j omega u j v. This is how we defined it last time, right? Okay. So, what happens, how does this guy map here? So, what I have is as epsilon tends to 0, the magnitude goes to infinity, okay, and the angle goes from plus 90 to minus 90. So, I will just have an arc like this, right, something like this. This is of radius infinity and it will travel in this direction, here, here, here and here. So, this is just to do with the pole at the origin, and the rest of the Nyquist plot follows the same procedure as before. Okay. So, if we remember the polar plot of this guy, it just looked something like this, right. So, the polar plot of 1 over j omega t plus 1 was something like this, right. It will asymptote here, this guy is t, omega equal to 0, I start from infinity, sorry, I start from somewhere here, I go here, and all the way I come back to omega is my plus infinity, right. And then if I want to do the Nyquist, I just take even the other frequency, right, something like this, right. So, this is how the plot will look like. So, this is what MATLAB will tell you, right, when you draw these plots, okay. And this we derived last time, okay. So, how do I really look at it, right? So, I start at omega equal to 0, or let us call it 0 plus, right. When omega equal to plus infinity, I will be here. When omega is minus infinity, I will be here. Omega equal to 0 plus, I am going here. Omega equal to 0 minus, so negative frequency, I will just be here, right. Now, what happens at omega equal to 0, right? At omega equal to 0, no sorry, so omega is 0 plus, go to omega equal to 0 minus, and then I have to really complete this thing, right, where, so this thing will be the region of infinite radius, okay. So, so this region is what I have to map now, right. This is what when epsilon going to 0, this little region, right, this also have to map it here, okay. And therefore, so the plot is complete by starting from here. I start at omega equal to 0 minus and go all the way, come to omega equal to 0 plus, and then go to omega equal to minus infinity, sorry, plus infinity, minus infinity till 0 plus 0, sorry, I will say it again, omega is minus infinity, 0 minus 0 and 0 plus and omega equal to plus infinity. So, if you draw on MATLAB, it will just give you this, it will just give you this line, these two lines, like this one, this one, and this the polar plots. It won't really give you this line because it won't be able to plot, but this is like this is just the infinite radius from here. Okay, I'm just drawing it very approximately, but you know, you could look at it this way. Okay, now the question is this system stable? Well, what was stability? I just look at encirclements of the -1 plus j 0 point, right. So, where is the -1 plus j 0? It is somewhere here, right. This is the point of interest. Now, what was the number of encirclements was n equal to p minus z. P is 0, z should be 0, therefore, the number of encirclements should be 0, right. So, since the number of encirclements is 0, you can say that the system is stable. Okay. Now, what if there are two of these poles at the origin? So, just do again the same kind of analysis. Okay. So, I am just dealing with this term now, right. So, I have limit epsilon going to 0, 1 over epsilon square e power j to theta, then epsilon e power j theta plus 1. So, this I am just looking this like this. So, with the k in the numerator, limit epsilon going to 0, k over epsilon square e power minus j to theta, right. So, of course, the magnitude goes again goes to infinity, and as theta varies from minus 90 to plus 90 in the S plane, the QS plane, it varies from angle of 180 degrees to 0 to minus 180. Okay. So, this is what then the plot would actually look like. So, what MATLAB will give you is these two, this kind of blue line here, right. So, I just go here, this I terminate here at omega equal to minus infinity, and this I terminate here at omega equal to plus infinity. I start from here at omega equal to minus infinity, end up here at omega equal to 0 plus. Okay. So, what happens later on is, again I am just looking at this as a thing of infinite radius going from angle minus 180 to plus 180. So, the plot is completed in this way, minus infinity, 0 minus, I go here, and do all the way. Okay. So, there is some kind of an encirclement. It is a little tricky, but it's you can just understand it how to complete these lines. So, what MATLAB would show me is these two things, right, starting from omega equal to 0 plus, omega infinity, minus infinity, and 0 minus, and these guys have to meet somewhere, right, and they will meet again via this expression. So, it will go all the way till infinity with this 180 to minus 180 and then come back here. Okay. So, what about stability here, right. So, this is how the Nyquist plot looks like. Now, can we infer stability of the closed loop system? So, again we look at the number of encirclements, right. So, what I am interested here is in the again the point minus 1 plus j 0, and if I see here that the closed loop encircles the point minus 1 plus j 0, this is our point of interest. So, if I look at it, well, it actually encircles it 2 times. So, the total number of encirclements is 2. Now, how many open loop poles are in the right half plane? Well, that answer is p equal to 0, and if the system were to be stable, what we need is n equal to 0. Now, n is not equal to 0, n instead is 2, therefore, the closed loop system is unstable. So, we could also look at it, if I look at it from the root locus, right. So, if I just plot a quick root locus for this, so I have 2 poles here and 1 pole somewhere here. So, well, on this side for all values of k greater than 0, my root locus would look something like this, and this we are plotting, well, you just say some non-zero value of k, my poles always will be here, and these are the 2 unstable poles which is also captured by Nyquist plot, and therefore the closed loop system here is unstable. Okay, so this is all about special cases of Nyquist. We will not really go into plotting complex plots. That's not the aim of the course of given a something of s power 4, s power 6, and so on. That's not important, right? So we just try to understand what these guys try to tell us. Right? Okay, so there is something also called as relative stability, right? So most of the times I'll say, well, I am interested in stability, the system is just about stable. Okay, so then the next question I will ask is how stable it is, right? If it is stable, will it remain there for all time, or will a certain change in parameter push it to the verge of instability, certain change in gain will push it to the verge of instability. So I want a reasonably good measure of how stable my system is. Okay, so what we know after we say, well, the first requirement is that the system should be stable, and next is to ensure that it is adequately relatively stable. Now, how does one measure relative stability? Sorry. Okay, so look at these two things, this brownish kind of color, I don't know what it's called. So this is a set of poles here, open loop poles, and these are also a set of poles, right? Now I go, so this is in my S plane, sigma j omega, these are the poles, are also called the dominant poles. I'll tell you later why I use the word dominant poles, but let's say the system just has two poles, and I plot the Nyquist for this, right? So this guy, blue guy goes here, and this brownish guy goes here. Now here I look at stability in terms of the distance from the imaginary axis, right? So if I am closer here, get closer until here, and there could be a point where I just tip off to the right side, right? Here and here. Even if I am just very slightly to the right, I am still unstable. Even if I lose by 1 run in a cricket match or 100 runs, I still lose, right? So the same thing here. Okay, so how does the Nyquist thing now look like? Here I just cannot directly measure relative stability. I can say, well, this is further from the origin, so it will take, it will still be safe if there are some change in parameters or things like that. It may just come slightly to the right, or maybe even move to the left, and so on. But I can say that this looks little more hopeful, the blue line, than the brownish one, right? This paired poles. Okay, now let's come back here, right? So what is the point of interest, right? So as long as P equal to 0, say the open loop system is stable, I just want Z to be 0, right? And if Z is 0, Nyquist tells me that the system is stable. Now who decides this? So so this is my guard, right, who says, well, you cross this line, you trespass, and you become unstable. So the idea would be, well, I'll just stay as far as possible from this line, this number, -1 plus j0, right? So look at the blue line here, it starts here and goes here, okay? The brownish line is still closer here, right? So this is this guy inside is the -1 plus j0 thing, right? And I want to stay away from here. Say something changes, and then if I could just maybe redraw a plot over here like this. So this is my point -1 plus j0, and if I do something like this, right, then I'm gone, right? Because I'm actually encircling the point -1 plus j0. Okay, I didn't really draw a smart picture here, but something like this. So I want to, so you could just see this one, right? If things keep changing, you may just tip over to up, okay? And then the what happens when I'm here, that is poles on the imaginary axis, I'm just here. So the Nyquist here, okay, I'll just draw it here. It will just be on this horizontal line, this and this, depending on omega increasing or decreasing, right? Okay, so based on this, can I quantify something as a measure of relative stability? Again, the idea is to stay as far as possible from the point -1 plus j0 or further to the left. Of course, you cannot really say that I will have pole set plus minus 1 million plus minus j whatever something, right, say j 10,000. This is also not practically feasible, right. So, we have to make some reasonable assumptions there, or to get some reasonable estimate of things. Okay. Now, what is then the beauty of the Nyquist plot? So Nyquist plot indicates not only whether a system is stable, but also the degree of stability. So, we will also see how it will give some information if the system stability can be improved, right. And then, since the deciding factor is this guy minus 1 plus j 0, and this entire stability criterion is depending on the encirclement of the point minus 1 plus j 0. So, what does the plot tell us, either the polar or the Nyquist, that as the plot gets closer and closer to minus 1 plus j 0, the system is on the verge of instability. Okay. Closer it is to minus 1 plus j 0, larger is also the maximum overshoot in the step response, and so is the settling time. Closer I am to minus 1 plus j 0, which means closer I am to the origin here, which means the damping is very small and things like that. Okay. Now, okay, so let us do it a little graphically. So, let us say this is not really, I am not interested really in the Nyquist, in the exact transfer function, but say something looks like this, right. So, this is the Nyquist plot, this guy, or even the polar plot. Okay. And this is the point minus 1 plus j 0, and I just draw a circle around here and say this is the distance from here till here is minus 1, the distance from here till here is a. So, what is this distance? This distance is when the imaginary part goes to 0. So, let me call say g of j omega, h of j omega at omega equal to omega 2, the imaginary part of this guy goes to 0, or in other words, even you can say that the angle would be 180 or minus 180 degrees. Okay. So, this is a thing here, right, at omega 2. Okay. So, what could happen that if this A is getting closer and closer here, then I can I am on the verge of instability. Say I have something like this here, okay, and say something changes, I increase the gain and I go here. So, once I go here, I am actually encircling this point, right. So, I will just go do some detour like this, and I can say that the system is going to the verge of instability. Okay. Let me erase these things because these are not important. Okay. So, there is something which this A can tell us, the distance or how far this guy is from this point. Not only that, now look at this circle and say, well, it intersects this guy here, right, at frequency omega 1, the magnitude of g omega h j omega at omega is omega 1, this guy is 1. Okay. Now, keeping this constant, and if I keep on moving along this line, which means I am adding some kind of angle to the system, right, I am just moving from here till here. Then if I add say some angle of phi in this direction, then I hit the point minus 1 plus j 0. Okay. So, once I hit the point, well, then I am on the verge of instability. So, there are two things, the distance or how far is this A from here, and second also how far is this angle from being minus 180 degrees, right. So, these two will quantify this A, and phi will give us some measures of relative stability. So far I just said, okay, just be further from the origin in the S plane. When I would talk in terms of poles, that the poles are they are on the imaginary axis, system is just marginally stable, slightly to the left, well, it is stable, but it is on the verge of instability, right. So, it is not very, so now I can actually quantify these things. Okay. So, let us say these things a little more formally now. Okay. So, the Nyquist crosses the imaginary axis at a frequency omega is omega 2 with an intercept of a, right here omega 2, and this intercept is called a. Okay, and then the unit circle intersects the locus of g h with a frequency omega equal to omega 1 here, right. And I just draw this unit circle because this is the point of my interest, right, the minus 1 plus j 0. Okay. So, the phasor of this makes an angle of phi in the negative real axis. Again, the usual measurement is we measure positively in the counterclockwise direction, right. So, this angle phi from here till here, and then well, this is now kind of known to us, right, and we know why this is true, that as the locus approaches minus 1 plus j 0, the relative stability reduces, okay. And this happens in two cases, right. So, this happens when the value of a, okay, this should be a little highlighted because it is in the, when the value of a approaches unity or phi approaches 0, or you know, so or this angle, if I measure from here the angle of g j omega, it should be minus 180. So, a approaching 1 would be bad news for me. In a similar way, phi approaching 0 will also be bad news for me, okay. So, therefore, we use this guys a and phi as a measure of relative stability, okay. So, we will use these two quantities a and phi to define the measures. Now, we will name each of them, right. So, this guy related to a we will call as the gain margin, and this guy we will call related to phi we will call as the phase margin, okay. The names will already tell us what they mean, but let us understand that in little more formally and little more details, okay. Gain margin, what is this guy? This is the factor by which the system gain can be increased to drive it to the verge of instability, okay. So, slowly we will try to understand. So, at omega equal to omega 2, this guy omega equal to, what is the phase angle? The phase angle is minus 180 degrees and the magnitude of g times h is a, okay. Now, I want to say, well, so say g times h, I will just not use this omega 2. So, g times h is a, I can add some gain, right, I can add some gain. So, there will be k 1 multiplied by g times h would be k times a. And I say, well, at what point does it reach 1? How much can I increase the gain factor? Well, that will be k1 is, if k1 is 1 over a, right, then g times h becomes 1, right. So, which means that if the gain of the system is increased by a factor of 1 over a, this is a k1, I am just multiplying again, right. So, don't confuse that with addition here, right. So, someone will say, okay, what is the gain margin? They will say, oh, this is 1, oh, how far I am? Just 1 minus a. You are not 1 minus a, because the gain comes as a multiplicative factor, right. So, here this way, right, if I add more gain, it will just show up here. So, this multiplied by the actual magnitude a, when does it go to 1? That goes to 1 when this additional guy here k1 is 1 over a, okay. So, if the gain of the system is increased by a factor of 1 over a, then the magnitude of g1 becomes a, this is the original magnitude multiplied by the new magnitude, right, k1 or the additional gain which we put 1 over a, this is 1. This means that the plot of GH, now again I am just not being a little lazy, not writing the entire thing of G, J omega, H, J omega, but that should be obvious, which means that the plot of GS will pass through this point minus 1 plus J 0, driving the system to the verge of instability, okay. So, therefore, now how do we define this? What is this gain margin in terms of a number, right? So, this gain margin may be defined as the reciprocal 1 over a, right, reciprocal of what? Reciprocal of the gain at the frequency at which the phase angle becomes 180, right. So, at this one. So, this frequency we defined as omega 2, right. At omega 2 angle g j omega 2 h j omega 2 was 180, right. So, at this omega 2 I calculate the gain. What is the gain at this omega 2? The gain at this omega 2 where the angle is 180 is A. Now the gain margin is defined as the reciprocal of this A. What is this A? The gain at the frequency, which is omega 2, at which the phase angle becomes 180. Okay? And the frequency at which this happens is called the gain crossover frequency. Omega 2 is the gain crossover frequency, and the gain margin here is 1 divided by A. Okay? So, by what factor should the gain be increased such that the system goes to the verge of instability? That is 1 over A. A again is defined at the value of G times H at omega 2. What is omega 2? Omega 2 is the frequency at which the angle becomes 180 degrees. Similarly, the phase margin. Okay, so we could just say, oh, now I understand gain margin, so phase margin should still be the same, right? So some similar definition. You say, oh, additional amount of phase lag needed to bring the system to the verge of instability. Well, this is vaguely true, but we need to be little more careful in formulating the statement or getting the exact value. So we will just see what are those steps. So okay, so first is, well, we are interested. Okay, let's revisit the picture again for a while. So what are we interested again is here, right? This intersection here, this phi, this guy I call this omega 1, and what is this omega 1? The point at which the magnitude becomes 1 here, this guy. Okay. So the frequency at which G j omega h j omega equal to 1 is called the gain crossover frequency, right? This is omega 2 where the magnitude is 1. How did we find this? Just by the intersection of the plot with the unit circle. Okay. So this is the frequency at which the plot intersects the unit circle. Of course, this unit circle is centered at the origin for obvious reasons, because we are just interested in -1 plus j 0, and we want to pull it along that angle to that point -1 plus j 0. Okay. And at this frequency, what is the phase angle? At this frequency, the phase angle, if you just measure, is 180 or even -1, either ways, right? 180 and this phi. Okay. Okay. Now, if an additional phase lag of phi is introduced in the system, right? If I just push it, this guy little up with an angle phi, the phase becomes -180. Okay. And while I am doing this along that unit circle, the magnitude remains unity, right? The magnitude remains 1, and once I reach that point where the angle is -180, what will be GH then? The GH or the plot of GH will pass through -1 plus j 0 once I have added that extra angle phi. Right? Just see this one, right? I am just pulling this omega 1 here along this circle, right? I am adding some 1 degree, 2 degrees and so on. I add 5 degrees, I end up here, right? What is the magnitude here? -1. What is the angle? 180 or -180, right? So I am just adding this extra amount of angle phi. Okay. Now this additional phase lag phi is called the phase margin. Okay. Now how do I compute this phi? Well, so now a formal definition is the phase margin is defined as the additional phase lag at the gain crossover frequency. Okay. And this is the frequency omega 1 where the magnitude of G times H becomes 1. So what we started off saying that, well, I need to add some phase. Okay. Now where do I add this phase? This phase, additional phase, I add at the gain crossover frequency. Again, the standard terms of measurement will be in the counterclockwise direction from the negative axis and so on. Okay. For stable systems, phase margin is always positive. That is maybe even true for the gain margin. Right? So if I just want to formally write down what is phi, okay, from that for which you think I had earlier here, this guy phi is the angle of omega equal to omega 1 plus 180 degrees. Okay. Now, let us see how this system looks like. So, now I have a system of the form, well, I have a pole at the origin and then to j omega t1 plus 1 and j omega t1 t2 plus 1. Okay. So, I can write this as or split this into the real and the imaginary part. Okay, I will skip this computation, but I will just write down the final value minus k t1 plus t2 minus j times k 1 over omega 1 minus omega square t1 t2 over, okay, bunch of terms in the denominator 1 plus omega square t1 plus t2 squares come here plus omega 4 t1 square plus t2 square. Okay, just check this computation for yourself also. Okay, so if I look at again that plot which I had shown, right, and if I say I am interested in finding the gain margin. So, at this omega 2 which I defined earlier, right. So, the imaginary part should go to 0. Imaginary part goes to 0 when this term goes to 0, this term goes to 0 when omega is 1 over square root of t1 times t2. Okay. Now, at this, so this is what, this is omega 2, right, at this frequency t1 t2 the magnitude is minus k t1 t2 over t1 plus t2. If I just put the magnitudes, it will just be the plus, right, this will go away. Okay. So, now for stability, what do I want if this is the point minus 1. So, this magnitude which is now this one, right, k t1 t2 over t1 plus t2, this guy should be less than 1. If I put less than or equal to, then there is some kind of marginal stability, and therefore, this system is stable as long as the gain k is less than t1 t2 sorry t1 plus t2 over t1 t2. Okay. See, it's quite straightforward. So, I start, so my thing is, well, I want to compute what values of gain k is the closed loop system stable. Well, so I just use this criterion, right. So, this how far is this guy from the point minus 1 plus j 0? How do I compute this? I just put the imaginary part of this guy to 0 and I compute the frequency, right. This frequency is omega 2, or what we call as the phase crossover frequency. What is the magnitude at this phase crossover frequency? It is k t1 t2 over blah blah blah. Okay. And the gain margin is this one, right. So, t1 plus t2 by t1 t2, and what we had defined earlier, this was 1 over a. What is a here? A is k t1 t2 by t1 plus t2. Okay. So, you just get the inverse of that. Okay. So, just to see some plots here. So, I start, so this is the same transfer function with t1 and t2 being equal to 1, and I keep on increasing the gain k, right. So, this is at some point here I reach the point minus 1, okay, and this point I can now exactly compute, right. So, k was what, t1 plus t2 over t1 times t2. So, at the gain k equal to 2, I just reach this point. These are all key gains for 1, 1.5, 1.75 and so on. So, as gain k increases, my my Nyquist shifts to this side, and if it is shifting to this side, I am reaching closer and closer to minus 1 to this. So, this was my omega 2 there, omega 2, and now I am here. Okay. So, this is will just show you how the plot changes with varying gain k, and how to quantify that. Well, that is this one, right, this guy. Right. So, this so what was this magnitude here? k T1 T2 over T1 plus T2. What happens when k equal to 2 and T1 T2 equal to 1? This guy becomes 2 times 1 by 2. This is 1. Okay, so that's what exactly is happening here at k equal to 2. Okay, I can compute it analytically and also check by the plots. Okay, so this thing we had seen last time also, right? So I had a system with an unstable open loop pole at s equal to +1. I had a 0 and this one. So, well, the system has an open loop pole at s equal to 1, and the plot. So this is the plot -1 plus j0, and I see that the plot encircles -1 plus j0 once in the counterclockwise direction, right? And p equal to 1. So what should n be? N should be equal to p for stability. P is 1 and n is 1. Therefore, the closed loop system is stable. Okay. Now, okay, what is the gain margin? Right. Gain margin is, we had said, well, reciprocal of A. How did we define A? A was defined like this. So this was A, this was the point -1 plus j0, 1 over A. Now, which means I am looking at the intersection with the real axis. Okay, now see where this intersects real axis. So it intersects here. What is the magnitude? Well, it's 2. Now, is the gain, so is the gain margin 1 over 2? Well, we'll see what that means, right? Okay. So if I start with gain of k equal to 1, sorry, I am somewhere here, right? This is the original plot, right? This plot, s plus 2, s plus 1, s minus 1 with k equal to 1. Okay. Now, oops, sorry, this is for k equal to 1. I am fine, right? So this is k equal to 1, n equal to 1 or n equal to p, where p was equal to 1. System is stable because I am encircling the point -1 plus j0, and I come down here. I say, well, k equal to 0.5. K equal to 0.5. Well, I am just here, just at the point -1 plus j0. Okay. K equal to 0.4. What happens? The k equal to 0.4. What is the number of encirclements of -1 plus j0? If I take this direction, well, there is no encirclement of -1 plus j0, right? This one. So n equal to 0. Therefore, system is unstable. Okay, what is happening here? Okay, now let's compare the root locus. Right, the root locus. Well, I have a pole at 1, another pole at. So I have. This is another pole at -1, I have a 0 at 2. Okay. So one pole goes to the origin, other goes. So this is starting from k equal to 0. I reach some point here, right? Let's say k equal to 0.5, and when am I stable? So what, under what conditions is conditions on k is the system stable? Usually, okay, let's then do something else, right? Say I have a system with a pole at -1, pole at -2, pole at -3, and there are no zeros. And okay, I'll just do all the rules of the root locus. So one guy will go to infinity this way, these guys two will meet here, right? So they do this way, right? So there's some value of gain k, say let's say some number, say k prime, right? This is k equal to 0. Right. So what are the values of gain k for which the system is stable? I will say for gain 0 to k less than k prime, right? If this is the value of the gain k when it intersects the imaginary axis. Okay, what can I say over here? Well, the system is stable. What happens for k equal to 0? K equal to 0, I am unstable. K equal to 0.1, I am still unstable until I reach k equal to say some kind of 0.5 here, right, where I am just at the point -1 plus j0 here. Okay. So this system is stable for k greater than 0.5, correct. So, I start with an open loop unstable system, I have to reduce, so the system is unstable until I have a certain gain. So, therefore, what we call these systems are as a system with a negative gain margin, right. So, the earlier problems were formulated in such a way that how much can I increase the gain k before it becomes unstable, okay. Now, it's the reverse, I am starting k equal to 0 is already unstable, k equal to 0.5 is already unstable, but there comes a threshold where after a certain limit I pull the poles back to the stable region and I am stable for all other gains. So, that is the concept of a negative gain margin, that first I have to make the system stable starting from an unstable open loop configuration, I increase the gain k and I push it to the stable region. Now, why is it negative? We will quantify that a little later while we do the Bode plot analysis in terms of decibels. So, we will stop here with the Nyquist thing. Again, getting or really spending time to get beautiful plots by just writing the imaginary and the real parts may not be very helpful, but this is just we have to keep in mind for our basic understanding, right. Now, we will try to do an equivalent version of the plots called the Bode plots, and there the quantification will be much more clear, the plots would be much easier. For example, here I really wouldn't know how does this cross here, right. There are also plots where you may say encounter things like this, right, like I am doing this and this and this and so on and something like this, right, much more complicated than what your driving exam would ask you to do. It just ask you to make 1/8 figure, here it will be several combinations of those. So, we are not really going to gain expertise on drawing these plots, MATLAB will do it for us, or there are several other tools also, right. So, once we have the basic understanding of the concept of stability and the relative stability in the frequency domain via Nyquist, we will go in the next class to see the construction of Bode plots. You might have seen this somewhere in your networks course. If not, then don't worry, we'll do it all over again. So, I'll just start with doing this on the blackboard first, right, just to slowly explain you the construction, and then we'll go to the MATLAB, and then I'll make some slides on that. Then what are the equivalent of how do I get gain in phase margin using Bode plots, and then lastly some interesting thing we also see is if I'm just given a Bode plot, can I reconstruct back the transfer function of the system, and that is also kind of pretty exciting, and that will give you an insight of I just start with a black box, I just do not know what is in the system, I give it several frequency signals, I construct the Bode plot, and I could kind of get an understanding of what is sitting inside the system, right. So, all these things we will do in the next class. Thank you.